beginning. So I'm Amit Apte. My main research interests are basically dynamical systems, data assimilation, and interface between probability and probabilistic approaches to data assimilation. I'm at ICTS here in in Bangalore.
Well,
Alberto, I guess.
yeah, yes.
Sandra Mitchell from MIT. I guess my field is systems control information theory. So, some physics. That's about everything.
Hello, I am Neeraj. I'm a research scholar in EC department at IISc. So I work on signal representations, compact representations, and I'm looking at speech signal sampling and reconstruction. So that is my area of work.
I'm Nitin Koshi. I'm a PhD student at the Department of Electrical Communication at IISc. I work in sequential detection problems with controls, with applications to visual search.
You heard me in the morning, Rajiv Karandikar at Chennai Math Institute. Probability theory and stochastic process, that's my wide area of interest.
Hi, I'm Shrikar. I work at TIFR CAM, which is in Bangalore. And my research interests are Gaussian random fields and general random fields and probability theory in general.
Hello, I'm Maithili Ramaswamy from TIFR Center for Applicable Mathematics. I work in differential equation, mostly partial differential equations like Navier-Stokes and other. I'm interested in the applications.
Yeah, I'm Gopal Basak from Indian Statistical Institute, Kolkata, and my area is like stochastic process and some application in different fields. So I want to learn some of these things what you are doing.
Hi, I'm Karthik. I work as a postdoc with Amit. Okay, my background is more in computer science and applied math, meaning my PhD was in machine learning, density estimation. Currently, I work in filtering and estimation theory.
I am Dan Christen. I work at Imperial College London. Does this work? All right. Yeah, so I've been working in stochastic analysis for quite some time now. The part of my research that is relevant to this workshop is particle filters, and I've been working on the theoretical characterization of particle filters. And in the last few years, I became aware of all these applications of particle filters and particle approximations and ensemble based algorithms into data assimilations, and I've been trying to talk to people that work in this area and convince them that particle filters are a viable alternative. Thank you.
I am Arya Paul. I'm coming from INCOIS, that is Indian National Center for Oceanographic Information Services. So what we're trying to implement ensemble Kalman filter in a ocean general circulation model. That's my research interest.
Yeah, I am Kunal Chakravarti. I am also from INCOIS Hyderabad, and it stands for actually Indian National Center for Ocean Information Services. So it's not oceanographic. So the same thing. No. So my research interest includes ecosystem modeling, and we are working on ROMS model. Both we are working on ROMS model, and our objective is to include data assimilation to improve our forecasting system.
I am Sarif, postdoc here, ICTS, working in discrete dynamical system and interested in data assimilation techniques.
I am Utpal Manna. I am from Indian Institute of Science, Education and Research, Trivandrum. So my primary research is in the areas of stochastic PD with application in the areas of fluid dynamics. So mostly I work on stochastic Navier-Stokes equations, some of the geophysical other models. So I thought of learning this subject as well because because the things I do is mostly theoretical. So I don't touch computer unless checking emails. So I thought of learning some of the applications. Maybe I'll do something in the future.
Hello, I'm Suresh Kumar from IIT Bombay. So I generally work on stochastic control theory. Current interest is in risk-sensitive control and its applications.
I am Ananya Lahiri from Chennai Mathematical Institute doing postdoc, and my research institute interest is estimation problem from nonlinear regression and some from finance problem.
Hi, I'm Arunangshu Biswas from Presidency University, Kolkata, and my interests are broadly in stochastic processes, statistical simulation algorithms like the MCMCs, and I want to learn a little bit of SPDs, and that's the reason I came to hear you.
Hi everyone, my name is Gugan Thope. I'm from TIFR Bombay. My research interests include stochastic approximation theory, and currently I'm working in optimization in very high dimensions.
Hi, I'm Chandrasekhar from IIT Madras. My major focus is in numerical weather forecasting and developing some nonlinear data assimilation technique for improving my cyclone tracking Bay of Bengal.
Hi, my name is Elaine Spiller. I'm from Marquette University, which is in Milwaukee, Wisconsin. I am trained as an applied mathematician, but sort of have moved towards a statistician. I'm really interested in applied problems. And in the context of this meeting, I work on some Lagrangian data assimilation, and I'm interested in sort of practical simulation type algorithms and developing those, and I'll talk some about that.
Hi, my name is Jesse Burwald. I'm from the Institute for Mathematics and Its Applications. That's at University of Minnesota. And I work in, I guess, sort of computation applied to dynamical systems, topological data analysis, and more recently some data assimilation. And sort of the common theme in all of that actually is studying parameter space. And so I'll give a little talk on parameter estimation through TA.
Hello, I'm Alejandro Aceves. I'm a professor of applied mathematics at Southern Methodist University. It's a university in Dallas, Texas, in the US. My area of research, my main area of research is nonlinear waves, mainly in optics. So yeah, I'm not a member of this community, so I just want to prove that it's never too late to learn something new.
I'm Colin Gredson. I'm a PhD student at the University of North Carolina, Chapel Hill. My interests are in dynamical systems, stability, and data assimilation.
I'm Sri Namachivaya. I'm from University of Illinois. I teach in aeronautics. I work in dynamical systems, random dynamical systems, and lately data assimilation. I got introduced to data assimilation, especially weather problems, because of Chris Jones in 2007. It's a very exciting subject. I'm trying to learn some data assimilation work in weather forecast.
Hello, I'm Noor Jaman from National Institute of Technology, Sikkim. So my area of research is experimental nonlinear dynamics and implementation of data assimilation in ROMS model, especially on for Indian Ocean.
Hi, I'm Ramon van Hendel. I'm at Princeton, and my interests are quite broadly in probability theory and related fields. That's all I have to say.
I'm Naratip Santit Tisadikon. I'm a postdoc at University of North Carolina, working with Chris Jones. My main research area is Lagrangian current structure to determine transport barrier in the geophysical fluid dynamics, but I has been working on data assimilation with Chris Jones for 2 years.
I'm Alberto Carrassi. I'm a physicist, and my background is in dynamical system, nonlinear system, but I've been working in data simulation for numerical weather and climate prediction since all my career so far, and I am now at the Climate Institute in Barcelona in Spain.
Okay, so I guess after lunch today and before lunch tomorrow, during the discussion sessions, we will have the shorter informal talks that we had asked. So those of you who have, so to say, send me an abstract or a title or something, please can we So I mean, we're just going to do it informally, so it's not really, we haven't made a schedule yet. So if you please come and talk to me, and then we can make a schedule right here on the spot. So those of you who are willing to do it, please stay here. We'll make up a schedule right now for today and tomorrow, so that then we can, so I mean, I think it's good to do it in the first half, so that then you can discuss with other people, those who are interested in similar topics. So those who are giving these talks, please stay here. And we'll have lunch at 12:30, that will be downstairs. And we'll meet after lunch at 1:30 for these short talks today. And, oh, by the way, tomorrow, I think tomorrow, or day after tomorrow, at 2 o'clock. Not part of the meeting, but there is a related kind of talk whose notice is put up on the notice board. It's, I think, data-driven models in biology, or something like that. I don't remember the exact title. I just saw it, so I thought I'll announce it. Just look at the notice outside. It's at 2 p.m. either tomorrow or day after. I do not remember. So, it's tomorrow? Ah, okay. So it was not in the schedule. Somebody else is visiting.
Keep asking questions. I don't mind that at all. That's the way it should be always. So, yes, it's informal, and as such, I also, again, the disclosure that or disclaimer that I made before is I'm a complete outsider. So historically, I got into modeling in climate at the beginning because of my student, Alisa Pampel. So all credit goes to her. She came to me and said, I want to work with you on a PhD. My expertise is lasers, optics. I was ready to give her a ton of papers to talk about things I know. And she said, but I want to work on climate modeling. And so I gave her the big things that were against that idea. One being, nobody knows me, so you're not going to get a job or anything from me by doing a dissertation on this. But she was stubborn, and we both learned together. So as I said, it's a very simple model. It's a dynamical systems-based model. And what I will do is glance up until people shut me down on some of the slides that are actually based on her dissertation presentation. So there has been discussions about timescales for weather, and just to highlight, when we talk about climate, not about weather, we're talking about trying to analyze behavior of in the scales of thousands of years, not days, weeks, months. And so it's a different time scale, and yet obviously underlying physics is very similar. The driving factor of climate that Alisa considered is based on the thermohaline Atlantic circulation. So it is this part of the overall circulation in the ocean. Red is warm, blue is cold, and there is surface, and there is, the overlap says that some things go at the level of the surface, some of the circulation goes at the bottom, and it is just the right balance that has warm water, 5 degrees warmer than in the Pacific, that makes living conditions in places where your family came from good, as opposed to looking at the same latitude in the Pacific where you don't see living conditions or not many people living. So is this balance, is this circulation what is driven by motion of water that carries water and salt, and the temperature that water has makes the bulk of the weather, of the climate conditions. So how do we go about studying this system? Well, as I said, flow is driven by density differences. And the density differences are due mainly to temperature and salinity. Those are the two variables that we're going to consider in our reduced dynamical system. Obviously, this is coupled with the flow in the ocean, the Navier-Stokes equations, and we will see how the strong assumptions and approximations that are made to reduce to a relatively simple dynamical system. Here is again the critical aspect of the sea surface temperature being about 5 degrees Celsius warmer in the North Atlantic compared to the North Pacific. That's the critical aspect of why living conditions are good in the areas such, that in Northern Europe. What can change density? Well, there could be evaporation that increases salinity, and and that induces and then cooling. The overturning component of circulation is the sinking of dense water in the high latitudes as it then moves south. There are models that can carry all latitudes from the south pole to the north pole. This much simpler model is just from the equator to the north pole, so only the northern hemisphere. And these are called box models, and they were initially built in the 60s, and they are still used to get some simple understanding, qualitative features. Clearly, they are far from being predictors. But the point of these models is to see the sensitivity and to what extent the circulation process can fail by changes in, for example, in salinity due, for example, to melting of sea ice and glaciers, or slow changes in the mean temperature of the annual temperature and whatnot. Okay, so it is a feedback mechanism, and as I said, the equations are Navier-Stokes equations on the top, incompressibility and the dynamic equation, and these are coupled through with temperature and salinity, which are classical diffusion equations, and convective part is driven by the circulation, the velocity field. And then you need an equation of state for the density that does couple this part of the equations with the Navier-Stokes. Then you begin to do simple models. So if you notice at this level, it's only ocean. There is no surface. There is no atmosphere. And it's only water circulation here. And so it's only the velocity field for the ocean, temperature, and salinity. The next assumption is assumptions on the equations for the velocity to lead to a system of equations for temperature and salinity. So because it's a short presentation in words, I will say how things go in terms of the simplification. So this would be a full 3D model in space, latitude, longitude, and depth in the ocean. There is going to be averages over longitude. The basic assumption within the range of the Atlantic is not much changes in longitude. So then you do an average over depth in the ocean. So you remove the two variables. So you are reduced to an understanding under one dimension, which is the latitude. So spatially, things reduce from 3 to 1 variable by these averaging processes. We remove all forces and diffusion for the understanding, the Coriolis force, not all forces and diffusion. And so all is driven by changes in density. And also we ignore gravity. So the only force is driven by density or pressure gradients, average over latitude and depth in the ocean. And at the end, you get a simplified model in which you can find a nonlinear function of the velocity in terms of temperature and salinity. Yes, yes, exactly. That's what drives the Coriolis force, exactly. Yes, P depends on rho, and rho depends on TNS, which is not written. There is a equation of state, but we're going to do the linearization. Rho is proportional to temperature differences and salinity difference, so it's a very simple approximation. So yes, that's where the coupling is. P is a function of rho, and through an equation of state, rho depends on TNS. Okay? Yes. Yes. Again, in words, I said the first level of approximations that lead to a simpler representation in terms of stream functions. That's the average over longitudes. Then at the next level, we remove these viscosity terms. And we end up with what is called a box model. So the box model is precisely, this is literally what you see in papers that study box models, driven, as I said, derived first in the 60s at Harvard by Stommel. And so you see here, this is latitude from the equator to the north, so we ignore the southern hemisphere. There would be some averaging in height, as I said, in longitude. You assume constancy in longitude. And so the top is the surface. You have about some average high temperatures near the equator, low temperatures in the northern hemisphere. You have a function that drives the circulation, that is the function Q. That circulation is driven by density differences. And then at the surface, you can have also a forcing term. F acts like a forcing term that is induced by, for example, melting of icebergs. So that is like a forcing because it reduces salinity. So the dynamical system is forced, driven. The motion is driven by a circulation, which is now an algebraic function of density, and density is given by an equation of state. And again, the simplest one you can write is just the linear approximation. Changes in density are proportional to changes in temperature and in salinity. Now you have a two-box model, so you're talking about two values, one at the northern hemisphere and one at the equator. And once you average in space, so you end up with a dynamical system. Now, the dynamical system is for the the boxes. So if you think about latitude, basically there are two scales, and the northern and the equator. So there is a 1 and a 2. Temperature, salinity. Here is the term that is driven by circulation. So Q moves warm water into cold water, or vice versa. It's, and the rate of change of temperature is given by the temperature difference, and the rate is proportional to the circulation. This is the tendency to go to equilibrium at the corresponding latitudes, and the rate at which it goes towards equilibrium. In terms of salinity, it's again similar. The same way that salinity differences through the circulation changes the rate of salinity at a given location. That's a term that is, again, similar. And then this is the forcing term that, again, is in the surface that could be done to, for example, melting of icebergs. So this is the dynamical system. It's nonlinear, but it's highly reduced. So if anything, one of the things I want to highlight that really wasn't mentioned much in the other talks, but it could be a point of interest when you go to more, build up richer models and think about timescales, the role of nonlinearity. Here, one of the things that we do is analyze timescales at the deterministic level. So far, think as this as a very strong simplification, all deterministic, reduced to a simple dynamical system. But now, one relevant piece of information is recognize the disparity of timescales that can happen in the system based on the physical assumptions that are kept. So you do a non-dimensional analysis and recognize that this is a two-time scale. There are two relevant time scales characterized by this small parameter alpha, which makes this in some ways a singular dynamical system. So this alpha is a large number, so there is a large number here where there is an order 1 coefficients in the second one. That makes multiple timescales at the deterministic level makes a first order simplification. So certainly when you talk about mixing now stochastic effects, data and whatnot, it is of interest, in my opinion, to see whether this multiple timescale analysis is well known for deterministic systems, how you can embed it into add the addition of stochastic effects. So what Elisa did is study this model for two different scenarios. So historically, the model had been studied for constant mean temperature and certain functionality of the forcing, which is now hidden in this variable p. So she did two studies. One is the role of yet another time scale of what happens if you have slow variations of the average temperature, some warming, what happens to the dynamics. And the other one, a little bit in the spirit of the last talk, the limitations of your models, of your deterministic models, can be then adjusted by stochastic effects. So there is certainly, you can put a time evolution of the forcing at the surface through, by adding more physics, but another way to do it is assume some random variation of this, now a parameter P or a time-dependent random variable P. So she did both of them, the analysis of this system in terms of slow evolution of the mean temperature and possible random effects due to the function P. Now, these are characteristic timescales. Where is it here? This is restoring towards equilibrium. If you remember in the original one, this is the restoring, the critical restoring time for equilibrium. Very good. So, and TD is the diffusion timescale, which you can imagine is much longer. Okay, 2 minutes. So, what is the essence of the model? At the simplest level, the model is bistable. So it says that the state of salinity, so Y is a non-dimensional salinity. There are two possible equilibrium states. One is the good one, where conditions are like the current conditions, and one is when all of Europe is covered by ice. So these are the two climatological effects. Is this nonlinear term. So if you so you write as a gradient of a potential. So this would be for theta constant. So whereas in the first case theta is constant, so this is if you write y dot is the gradient of function v. So this is the potential, and as I said, there are two states, and climatologically we know for a fact this is not made of. In Europe you have the current state and the state where Europe was covered by ice. So it would be terrible if you would have, in the deterministic case, if you are at the minimum, you stay there. But if you have fluctuations, if it is stochastic, you can see what the role of the stochasticity is to jump from one state to the other. If it is slowly varying, which is the case that she studied, there is a parameter mu, and there is a parameter theta, which here it doesn't quite appear because it's average over theta equals 0, but if you put the theta dependence, you can have V to be slowly varying in time. That's due to temperature, so that changes the potential. Or you can have the role of stochasticity in P and understand the conditions and the time jumps, how long does it take to jump from one state to the other. And so let me finish with highlighting, for example, a simulation where you do P, the freshening of water, as a Gaussian white noise under certain variables closely related to physically realistic situations, whether indeed you have these jumps from one state to the other. Obviously, she did an analysis on the probability distribution function of this now variable V, and how likely it was to change from one state to the other. So there is this stochastic freshwater perturbation theory she did, and then there is the slowly varying modeling that is due to changes on the theta function, the mean temperature over for different functional forms of temperature. And again, she saw in the case where theta was time dependent that this bistable state that you see here disappears to a single state. So there is this open question about a big climate change. Is it stochastic, or is it a slowly elimination of the bistable state suddenly, going into one state, and if the state is the icing state, that's what you could see, in a few hundreds of thousands of years. So at least for the time of this conference, we're in good shape. But who knows, for a few generations what will happen. Thank you. Yeah.
Which has important implication in the distribution in terms of extension and thickness of the sea ice that are
Good, good. And as I said, I mean, we understand as he says, I mean, he talked about even richer models, and there is a point in which you have to stop and say, this is as much as far as we go to with the deterministic models, and then how you enrich through other things. And you're right. I mean, whether you can make more layers, more boxes, you can analyze things like that, and that's what we're looking for. And again, in particular, one of the questions in our language of the multiple scales. The multiple scales is natural in a deterministic system. Even if you make approximations, you can recognize when you do non-dimensional analysis. But when you, for example, reduce a model and then put stochasticity or put the stochastic nature of unknown data with precisions, and then there is a time variability that is very different, I don't understand. I mean, it's not clear to me how you do it. I mean, it's non-commutative, which things you do first, how you do averaging first when you have multiple scales, even at the deterministic level, in addition to the characteristic time scales of random temporal distribution, temporal variations. Yeah. Thank you.
Hello. I'll be talking about a scheme for data acquisition which comes much before we start analyzing the data. So the topic stands far from the discussion going on here, but as it is it's a fundamental issue when we process data. So I thank the committee to give me an opportunity to share this. So when we get any continuous time data, the first thing we do is sample the data so that we can do processing on the discrete data set. So the issue of sampling is fundamental for processing any data. So we have a continuous time data considering one-dimensional data. So why we need to sample is because we need to store the sample. So we have a storage limitation, and we need faster and reliable computation. So we need a finite data set, and we want to transmit data, and we have physical limitation in capturing data. We cannot capture the continuous time data. So both hardware difficulty come as well as computational issues come. So the intuition to sampling is, suppose we have an elephant and we send a few blind men to understand the elephant. So everyone will catch some part of the elephant, and each one will have its own interpretation about the elephant. So someone can say it is a spear, it's a fan, or it's a wall. So these all are, so the question in sampling is to understand the whole elephant from its parts. So that is what we do in when we acquire data. So this continuous time data comes and we sample it using some kernel. Here the kernel is a uniform sampling kernel, which is sampling at Nyquist rate of the signal, and which is dependent upon the bandwidth of the signal. So out we get are the discrete samples. So now once we have these discrete samples, Shannon's sampling theorem states that if my sampling rate is greater than the Nyquist rate, I can do signal processing with the discrete sample sets. So we go back to this and ask that, so what are the approaches available is, we have Nyquist sampling. So recently random sampling has been proposed, which uses compressive sensing framework. I'll come to that. So we propose, before that, just what is uniform sampling. So this is my continuous time signal. I have a clock to sample the signal at the front end. So the clock will, at every time TS interval, it will pick a sample from the signal. And I will have this as my data set. So instead, we go back and say that, can we non-uniformly sample the signal? So instead of uniformly picking up the samples from the data set, what will happen if we pick non-uniformly? So why the motivation for that is, suppose we have a signal and I want to capture the signal only when something is happening in the signal, not all the time. So when I sample the signal uniformly, irrespective of anything happening in the signal, I am always taking up samples from that. But instead, if I pick non-uniformly, I can design an event-triggered scheme in which when that event criterion is satisfied, at that instant only I will pick a sample from the signal. So that is the motivation. And so the question asked then, why should we go for that? So this is the scheme here. So I have a signal, I have a preset event. So the signal passes through an event detector, and the event detector will detect did the event occur, and if it occurs, a sample will pop out. And here I also need the time instant of when the event occurred, which was not there in the previous case. The previous case, I know that if my sample is n sample, then it is nts is the time at which it has been occurred. So, this is one example of level crossing. So I have a level here, preset level, and whenever the signal crosses this level, I will capture these samples. Similarly, I can capture at the extrema of the signal. So these are the extrema points. I will capture the signal only when an extrema occurs in the signal. So this can be contrasted with Shannon sampling as to be non-uniform, and it is non-linear because it is a detection-based approach, not a kernel multiplication-based approach. So if we can do that, then why to go ahead with this approach? The question is, so if we design event, then the event should be robust to noise, because if I am capturing, if I say that this is the event, the signal can have noise, and this noise can influence the occurrence of the event. So the event which I set, yeah. Yes, yes. On the hardware, how do I do that? Yeah. Yes. So, yeah. So that limitation comes when we are in discrete time processing. We can design analog circuits which will get activated only when the signal crosses this level. So we have op-amp circuitry which will fire only when this threshold is crossed. So the motivation for such events is the neurons in humans fire when such events occur. Like whenever the voltage crosses this much level, a firing will happen. So that's why we choose these as the basic. These are very simple events. So the extrema can be set as zero crossing of the derivative of the signal. So derivative can be done in analog domain by some analog circuitry, and we can capture the zero crossing of the derivative as the extrema occurrence. Yes.
Extremely non-robust.
Yes. So yeah. So, but I will consider a case that we know the bandwidth of the signal. So we will have a band pass noise. So if you have white noise, then every change will be a extrema. But when you have a band pass noise and you know the bandwidth of the signal, so we try to understand within that bandwidth how did the noise play a role.
If you know the bandwidth of the signal, then is it microsampling, or else the question would be,
Yeah.
isn't that what the Shannon theory says?
So Nyquist sampling will not allow us to subsample the signal. So whereas in this scheme, I can subsample the signal. So in Nyquist rate, my sampling is always above the Nyquist rate. So number of samples is more. But in this, depending upon which event I choose, I can get subsamples. So my storage may be reduced. And then the question is, can I recover the signal from those subsamples? So how to address that question is the work about it. Suppose we go ahead with such method, then can we recover the signal? And another interesting question which we think is relevant is Nyquist sampling is focused on full signal reconstruction. But in many cases, you do not want to reconstruct the full signal back. You want to estimate some parameter of the signal. So in such cases, it's not relevant to capture the signal at a uniform rate. Instead, you should sample the signal such that you can recover that parameter of the signal only. Yeah, so which parameter you want? Yeah, so in Shannon, okay, so the bandwidth of the variation of that parameter, you mean? Yeah, that can be used, but I have not come across any approach taking that. If you know the bandwidth of that parameter, how does that parameter affect the signal? So one case comes when the signal is time varying. Suppose it is a chirp signal. So the frequency is varying with time. So in that case, you can sample at the frequency innovation rate. How is the frequency changing? So I want to quantify the change in the frequency only. But that will affect the whole signal. Am I clear? So suppose I have a tone signal and it's a constant frequency tone. So just capturing the zero crossing of the signal will give me what the frequency is. So but if the frequency is varying with time, then also if I capture the zero crossing, I can get to the frequency of the signal, the time varying frequency of the signal. Whereas Shannon will say me that capture at the bandwidth of the signal, which is quite high when the frequency is varying with time, because it's no more a band limited signal. So the question we address is, are these samples robust to noise, and are they robust to jitter in the signal, in the detected instance, and the feasibility of signal reconstruction and performance of these methods for signal reconstruction. And the last question is reconstruction actually needed, because you need not reconstruct the whole signal to get some information of the signal. So this plot is a simulation plot of showing how are these instants robust to noise. So the blue one here is the zeroth level, and the cyan one is level crossing at 0.8. The signal is normalized to plus minus 1. So with increasing level, this robustness to noise decreases. So y-axis is the average perturbation of the. So I know at what instant the level crossing occurs in the clean signal. So with noise, how much it has perturbed. So it's a variance of that. So using a Monte Carlo, it has done. So with increase in level, so the variance increases. So as I move far from the from zero level, the effect of noise increases. So that is happening because my slope is higher at 0 if I see the signal, and as I move up, the slope decreases. So if I add a noise, there will be less perturbation in time when the slope is high, because it cannot pull down the. So the noise is band pass noise. So we have to see how the band pass signal is adding with the signal. So this is what this plot is saying. But interestingly, at how slope is. Yeah. So yeah. So that example was for, I was explaining for a single sine wave. So for a single sine wave, slope is always maximum at the 0. So when you have sum of sine waves, the slope can be anywhere maximum. Because yeah. So what we did we analyzed this performance, and it doesn't depend on the amplitude of the signal, but it depends on the slope of the signal. That is what we found. So mathematically, it can be shown that the slope is affecting. So, but when we have a sum of sine waves like this one, the slope can be maximum at any place. It need not be maximum at 0 crossing. But when you have single sine wave, to understand it, you can see it as a single sine wave. So interestingly, at extrema, it drops down again close to 0 crossing. So extrema, you can see that with increase in level, it increases. But extrema, it doesn't go beyond 0.8. It falls back to inside. Yeah. To. Yeah. Yeah. Yeah, I have not linked with that. So I will see that. Yeah. Number of zero. Yeah. Okay. 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 Yeah, Gaussian. So for extreme also it does. I can see it as 0 crossing of the derivative of the signal. Yeah. Using that, I can add it. Okay. Okay. Let's see. Yeah. So the second one is a jitter in the time instant. So once I have captured the time instant, if I jitter the time instance, if I add some noise to the detected time instant, how does the recovery affect how robust is the recovery to the jitter in the time instance. So I'll come to how I recover, but this plot shows that extrema instance are more robust to jitter. So this is my extrema ES, this is the blue one, and these all are my level crossing at different levels, 0.001, 0.13. So and this is the perturbation factor in the jitter, and this is the probability of recovery of the signal. So probably one means that I have recovered the signal perfectly. So as I increase the perturbation, the recovery decreases, but the recovery is faster in level crossing compared to extrema. And this DYLC is the dynamically chosen levels close to extrema. So when I am close to extrema, if I have perturbation in the detector, so why I want to add perturbation in time instant is, suppose I want to transmit these time instants, because I have to encode the time instant as well when I want to send this information. So if there is a noise in the time instance during transmission, which technique is more robust to that sort of noise? So extrema is shown to be robust here. So this effect is contrasting with zero crossing, where zero crossing was robust to additive noise, whereas extrema is robust to jitter in the time. So this also can be understood if we plot the time instant, the signal, and see that the slope is minimum at extrema. If I see here, slope is minimum here. So if I jitter the time instant slightly, I will have a less fall in my amplitude versus if I jitter the time instant here. So when the slope is less, the fall in amplitude. Yes? Yeah. So if I jitter the time of extrema occurrence, by zero crossing of the derivative of the signal. So, so if I jitter the time instant, I will fall less in amplitude if I am at extrema versus if I am at level crossing. So, the next question is can I? Yeah. So I have captured the sample, the data set, which the data set is composed of these instant, this sample, and at these instant the sample occur. So using that, can I recover the whole signal back? So yeah, reconstruct. So why I want to reconstruct is, so when you have non-uniform samples, doing data analysis in this type of data set is not well defined. So you cannot do spectrum analysis of such data sets. So what you do, you go back to the signal again and through some interpolation method and get uniform samples again, and then do data analysis on such data sets. So, so why then do this? Just go with uniform only. But when you go to hardware, these techniques are much more simpler to apply on hardware. So it's coming up now that hardware can be realized right now. So just one more plot I want to show. So this is the sampling density plot. So so this plot shows that if I have an extrema among the zero crossing, level crossing, and extrema sampling, how many samples do I get? The sampling density of such methods compared to Nyquist sampling density. So if I am above the Nyquist rate, then there's a Landau theorem which states that if you have sampled a signal at greater than Nyquist rate, you are guaranteed to get perfect recovery. The method how you can get is not there, but it guarantees that you can get. So we can see that this black dot is the Nyquist density versus bandwidth of the signal. So all these methods fall below Nyquist density as the bandwidth increases. So but as I keep on taking higher derivatives, it goes closer to the Nyquist density. So there's a theorem called Logan's theorem on sampling density for using zero crossing. So this we are seeing that for higher order zero crossing also there's a possibility to extend that theorem to extrema and beyond extrema. How does the zero crossings behave, rate of zero crossing? So using this, we go ahead. Yeah, so this is level crossing 0.3. So when I have a level crossing, so level crossing, when the bandwidth increases, the signal will fluctuate more. So the level crossing is not a reliable sampling scheme because you don't know when will it cross. But zero crossing you are always guaranteed, it has a relation with the frequency content, and extrema also has a relation with frequency content. So that is why they behave monotonically increasing, but level crossing falls down. So then we go ahead with this to see the recovery. We model the signal using trigonometric polynomial. So it comes down to a linear formulation once you have acquired the signal. So this is my acquired samples. This is my model, and C is what I want to recover. So once I have recovered C, I can reconstruct the signal back. So here we use sparse representation approaches to recover C, because sampling density need not satisfy Nyquist rate. So we go ahead with a further imposition of a structure on the signal, that is a sparsity structure, and propose recovery using. So I'll be happy to take any questions anytime you feel like asking. Yeah, so if C is not sparse, then it's a ill-posed problem. You cannot recover when you have subsamples. So you can see it in a linear framework that if you have y equal to ax, you need at least at least that many number of rows. Yeah. So because we don't have adequate number of samples, so imposing sparsity criterion enables one method to recover the signal back. So it's not the only method. No, it need. No, it need not. As you can see here, when I'm at 3 here, bandwidth ratio is 3. My this extrema sampling, that light green one, that is giving me more than Nyquist rate. So it is above. So it need not be always. But we are considering the worst case, that if it is below also we can recover. Thank you.
So good afternoon. So my topic is implementation of data assimilation using ETKF, means ensemble transform Kalman filter in ROM's model for Indian Ocean. So this is the talk with Amit and Vinay Chandran earlier. Okay. So I will say briefly why data assimilation, then what is ROMs, then data assimilation, and how we are implementing ETKF using ROM's model, and the problems. So this is the typical salinity in ocean. So this line indicates the model salinity profile with depth, and this is the observations, and the temperature with depth from model is like this, and from Argo float is like this. So we have deviation from observation and models. Both have deviation. So the idea of data assimilation is how we'll eliminate all these errors. So this is one, and another one is, this is the sea surface temperature at Indian Ocean near India. So you will see that from climatology, so first is model, then climatology, and then the difference. So you will find that there is a difference. So how we will eliminate those problems? So these are the things we have to eliminate, and that's why data assimilation is introduced. Now, in case of ROMs, these are the equations, and hopefully we had earlier we have seen all these equations, and these are the modified Navier-Stokes equation for Indian Ocean, and all these are partial differential equations. So these are this is the pressure term, eddy viscosity, diffusion, and other forcing term. So this is the model equations which is solved on the grid on Indian Ocean. These are pressure and continuity equations. Okay. So the model is solved in this domain. So this is the full Indian Ocean, where it is divided into different domain like this and then solved. So in our case, what we did, this is a 0.25 degree model, and these are the domains, and vertical layer were 40. So definitely solving this kind of problem is not sufficient for a single computer. So we used cluster, and in that case, this show the model run, ROM's model run versus CPU time. So with number of processor, it decreases. So we used around 8 core per domain. Okay. Now, in earlier talk, we have understood what is data assimilation. So ideally what happens, from one time to another time, model runs, then we stop. Then what we did, we have observations. So in this case what happens, we have observations from floats, especially here we used salinity and temperature. So that we assimilate through certain scheme, that is ICTS-TIFR, and then we correct the initial condition and then the model run. So in that way, data assimilation takes place. So these are the Kalman formula for the, so XA. So I think we know, and we have just learned from earlier talk that X is the analysis, XF is background or forecast, and Y is the observation, and then this Kalman gate, and this is the forecast covariance and analysis covariance. And if we, so in our case what happens, this is almost 300 by 340, so, and 7 variable, so it is almost 10 raised to 7 state dimensions. So it is not easy to just implement Kalman filter directly. So, and that's why we implemented ensemble transform Kalman filter, and these are the final form of update equations. So ZA is the update from background with this transformation, and the ZEF comes from our ensemble. So we have different model run from where we have ensemble of states, and that the difference between mean and the ensemble state is delta XF. So that constitutes ZFE and ZFE from where we are getting all these things. So finally, we are using basically these equations. ZAE equal to A is the transform matrix, and operated on ZFE. The ZFE is basically our states, anomaly in states, and the update mean is this one. In this case, we used, in our case, what we used 60 to 80 ensemble we tried, and in that case, we used 480 cores or like that. So now, in actual problem, how we are going to form our ZFE. So in that case, what we did, so we have model run. From that, we have temperature, salinity, horizontal velocity, that is U and V, and dynamical ocean height. So 1, 2, 3, 4, and 5. These 5 variable at each grid point. So at each grid point, we have 5. So that constitute our one vector. So these are one vector, and for different run, we have different vectors. Sorry, this is the vector. So each time we will get one vector. So this constitute our ensemble. So this is basically difference between anomaly, difference between state, model state minus mean. And the observations are the data from Argo floats, that is basically temperature and salinity from each profile or float. Now, in this case, what we suppose we are assimilating for one day. Say we are assimilating after one day. So from this 0 to 1 day, all observations are going as observation to the model. No, so that I am telling. So suppose the model goes from 0 to say 1 day, now we stopped. So the data from this to that is considered the data at that point. Or we can take observation from say plus half day and minus half day around that point, unless it will be, sorry? So 1 day in this case. So the okay, so then we did the data assimilation for Indian Oceans, and the first column shows the update of SST. Okay, so this is the assimilated thing, and this is the model run. So in our case, we have a lot of oscillations, and it looks noisy, but the model is finer. So this thing we have to still address this problem, how we will tackle. So this is the one case, this is the assimilated, and this is a model run. Yeah. Sorry? Okay.
If I look at these two plots,
yeah.
despite of the difference in scale,
Uh-huh.
that you say, one thing that you want to see is the ICTS solution is closer to the observation than the run on the left, on the right column. So you cannot assess this from this plot.
Yeah. So it is difficult because see, in our so yes, we are just showing model thing, how model shows the temperature, SST, and the assimilated thing, how it looks like. It is okay, yeah, the kind of, but it is basically model run. Prior. So, okay. Now to eliminate the noises, because the main problem was there, we have not localized the effect of observation. Suppose one float is here in this, but this should not affect the temperature here, but due to spurious correlation it is doing. So, sorry? Interpolate means, no, it is not interpolated. It is not interpolated. No. That is the main problem. So, yeah. So to eliminate that effect, spurious, so what we did, we try to do localization using some Gaussian function. But in that case also we found where the floats are there, we have divergence. So still we are not getting optimum things, we are trying. So, large.
There is a large bias in the model, because of which the innovation is very large. So the uptake is quite fast. So there is a, due to localization, there is a large jump that happens. So that say instability that gets created, and then you are maybe smoothing or something like that. Which way it is?
So okay. So So these points are basically the position of our observations. Some Gaussian function use. So that see, the practical thing is that suppose we have a float here, so this should not affect here. So the effect should be died down by using that one. Still, this. So the float actual observations are. So we allowed such a way that this area should be affected. So still the problem is inside that radius of influence it is diverging. So that is the problem.
How did you choose the correlation length? How much area it should affect?
This is a good question, but actually this we did ad hoc. So 100 kilometer or 50 kilometer like that. So maybe the ocean people can tell us what will be the actual correlation length. So
now the localization here is essentially done from the ensemble base of X. So you left multiply, I guess, from a function
yeah,
which represent your base of X score product of
a sort product basically.
you make this Gaussian or whatever. That's what they are doing.
Yeah.
So we are still doing a global data analysis by localizing the way.
Yeah.
Okay. So it's not a Logan sample transfer.
No, it is not a LTPF. Yeah, with localized different. Sorry.
You really only have like 7 observations or something like that. I'm counting the red balls.
Yeah, 9, 10.
Any hope of having meaningful information from those that little data? I mean, it seems that they're much more part of the correlation rate compared to the.
That will be yes. It's 2 hours. So Indian Ocean has 10,000 kilometer and we have 9, 10 data only.
We have 3,000 floats right now.
3,000, yeah.
Over the ocean. But in the Indian Ocean, we only 7.
Per day or per 2 days.
So
what I'm trying to ask is there any
you get a few of those. So the lesson is to now include it was clear that the data is included extremely sparse, and what we need to include is some other data sets like SSP or surface height or something else along with
small swath, no?
Sorry?
The small swath, small swath.
Yeah. No, but now you have around 300, 300.
I was close to there.
But not every day.
you don't have every day. That is the problem.
Even you will get a ticket product itself for the entire basin.
Now there are these graded data sets available.
Now that's already.
Oh, then okay.
But those are tabular rich.
Yeah. But my question is, from this data that you have, you're having lots of data, but still.
No, we should not get meaningful.
But forget about that.
2008 or so we had downloaded this data.
But Amit, Raman's question is that this very little data is there. It will not get meaningful. No.
Try to see what happens to any filtering technique if you have extremely sparse data. And you can see the optimal flow.
The situation,
One should ask where to place them.
if we have small amount of sensors, maybe what you should ask actually is how to optimize the placement.
Which is not
Sorry?
These are Lagrangian floaters. You can't do it.
Yeah, Lagrange.
They're not fixed.
So they are Lagrangian float. They are moving. They are going deeper, then moving, then coming back like that. So okay, the same problem in U and V also. 60 is how many ensemble we have used to calculate this thing. So a number of ensembles. So so these are the results so far we have got. So still we have many problems. So especially the estimation and validation of error covariance from model and observation. So what is the error in model also? So that Q, how we will determine, that is also another problem. And also the another problem is how we will incorporate more observational error. That is another problem in float data. So what will be the error? So that is also another problem in this case. Design effective initial perturbation fields. So far what we have got, we made an noise, so we added some noise with a particular model run, and that was our initial condition, initial ensemble. But is that good thing to do? So that scheme also we have to consider to get effective data assimilation thing. And also the proper covariance localization finding, this is also important. So this thing we have to, and also the develop of an effective DA system for Indian Ocean to improve the forecast. So if this problem are solved, then we can already be able to do this thing. So okay. So okay. So this is different. So in bigger system it is difficult. So we tried in Chua model also. This is basically Lorentz kind of system, and we did in a small model where we used some model generated data. So, and this is the talk. Thank you. But then it will not be problem in model run. So when model will run, if you correct the climatology, then it will be problem. Will not be. Model again.
What is the expectation in terms of forecasting, and in particular in terms of
That I don't. That I cannot tell right now. But okay. So object. So actually, basically, so in what I'll tell. So if you can predict the SST, if you can predict sea surface SST, sea surface temperature, then you can at least predict the typhoon or this kind of thing, whether it will form or not. So there is some theory like that. If it is more than 28 degree temperature, 28 degree centigrade, then it may happen. So that way you can predict those things.
there are other applications where if you can better your current prediction, then that can be